In previous videos, we talked about probabilities of discrete things. And we used, this notation here for a probability of a single random variable x. Little p for the probability, x for the random variable x, big X. We use capital letters for random variables. With the argument little x, the little x is the realization of the random variable, what you might actually get. And here was the notation for the joint random variables, where you have two random variables x and y. Anyway, that was the notation. And by discrete, we mean possible arguments are not connected together. Like they came from things like a coin toss could either be a head or a tail, or a die toss could just be 1, 2, 3, 4, 5, or 6. What if you have something continuous, like you throw a dart? How far is it from bullseye, the center of your dartboard? That's a continuous variable. How do we deal with continuous variables? Well, we define this thing. We call this thing the cumulative distribution function, capital F. And it is defined as the probability that your random variable is less than or equal to some argument you give it. And that's what we call the cumulative probability distribution function. Here is its notation. Cumulative PDF, cumulative distribution function, capital letter, random variable x, the realization little x. There's a bunch of things that can be derived about it. I'm not going to do the derivations. It's for a more thorough probability course. But it is a strictly non-decreasing function. Further you go to the right for your argument x, the more this f of x goes. If you take the limit as x goes to minus infinity, you get 0. If you take the limit as x goes to positive infinity, you get 1. Non-decreasing. Its value is greater than or equal at a higher realization or argument, at a bigger argument of little x is greater than what it is at a smaller argument of x. That just means it's non-decreasing. The probability that your random variable lies between two numbers are actually greater than the lower one and less than or equal to the bigger one. It's just this difference. So if you want to know what's the probability that your random variable x is between this x and that x, this difference of the cumulative distribution function. And here's a big deal. The probability density function is defined as the derivative of this distribution function, where that derivative exists. Keywords: distribution versus density. This guy is kind of analogous to the little p's we had for discrete probability. Except you'll see that it doesn't have a particular value. You need to integrate to get anything. Here's some properties. If you integrate that PDF, the probability density function, up to some x, that's probability cumulative distribution function. You'd get this probability that x is within some range, by integrating the PDF density function between those two limits. For a proper PDF density function, the argument should be strictly non-negative, and it should integrate to 1 if you integrate it over the whole real line over all possible arguments. And we could have joint PDFs, function of two random variables, x and y. I won't go through this definition, but here's the big concept, and it's students have a little trouble getting in their head. You want to know if x and y lie within some region in the xy plane, the probability of that, oh, my computer's breaking up a little bit. The probability that x and y lie within some region of the xy plane is this definite integral. You integrate the joint PDF over that region. And the big thing that it takes a while for students to get is you're often not asked for what's the probability that x is within a certain region. You have to translate the problem statement into that region. It might say, what's the probability that x is greater than y? Or what's the probability that x and y are within some circle, that x squared plus y squared is less than 1, for example. You'll need to translate that into a region of the complex, not the complex, into the region of the xy plane and take this definite integral. So that's a big key to doing these type of problems. And I will, oops, before I get to that, well, I'll do some examples in another video, otherwise this goes on to things carry over like they did for discrete probability distributions, conditional probabilities. Same relationships carry over, just like they did when we were talking about sets and events, subsets. And same with Bayes' rule, it holds for PDFs, density function, probability density function. You're going to hear me say PDF a lot. That means probability density function. And a lot of what we're going to do dealing with continuous probability density function. In fact, from here out, most of this course will be dealing with continuous random variables. The discrete random variable stuff is kind of good for talking about getting an intuition for some of the probability concepts. But from here out, we're going to be doing almost exclusively continuous random variable stuff. Independence is the joint PDF product of the individual PDFs. If that's true, then they're independent. If they're independent, then that's true, if and only if. When we're finding the marginal probabilities and discrete probabilities, we summed over either a row or a column in that matrix. If you go back to the previous video, now those summing operations are integrations. If we're given the joint PDF of x and y, we just want what's the PDF of y itself. We do this integration. We integrate the x out of it. And if we want the PDF of x alone, we integrate the y out of it. So these are things that will go on a formula sheet. What might a joint PDF look like? I can only draw it if I have two random variables. I think I have x. I think I have x going this way and y going that way. The joint PDF, in this case, kind of looks like this mountain. This looks like a joint Gaussian, but it wouldn't have to look like that. What you're looking at is some thing in 3 dimensions. For every x and y, there's a value. It's a surface of some kind above the xy plane. That's what a joint PDF of 2 random variables looks like could look like. If you have 3 random variables, I can't draw, it's too many dimensions. I won't do this example just yet, but this is a case where the joint PDF is this sort of prism, this rectangular prism. In this thing, it's this sort of Gaussian mountain. We'll do the example in a future video, and we'll get to Gaussians several videos down from here. It's the introduction of continuous rings.